Welcome back. So in this lecture, we would be looking at an important topic. It has a lot of utility. For most of the calculations, we'll be using this concept of equation of state. All right. So first, let's understand what's not an equation of state. Okay? There are equations and there are equations. Okay, there are certain equations which are very fundamental. For example, in classical physics, all the equations are summarized here for this from Feynman lectures in physics. Okay, these are very fundamental equations. But what we are going to discuss here doesn't have that status, but it has a lot of utility. Okay. So first, let's ask, what if we didn't have equation of state? All we would have had is a huge table, okay, with pressure, temperature, and specific volume. Okay, so if you had this, okay, so that has certain utility. Okay, so that's a poor man's equation of state in some ways. Okay, so all you had at this table, that's a huge amount of data. Who cares about that data? That can be quite useful actually, because supposing you want to ask this question, everybody probably has seen a cooking gas cylinder. So what is this contraption? It is a cylinder of a particular volume. Volume is fixed. It's a container which doesn't, not a flexible container, it's a steel cylinder, let's say. Its volume is fixed, and you know at what temperature you want to be operating, right? That's your kitchen temperature. Okay, so you know that also. So given these two, supposing you want to fill up till what pressure, how do you correlate? And it comes at a particular pressure, right? The cylinder comes at a particular pressure. So these three things are correlated in some way, right? So how much of, and for a given volume and a temperature, if I say I am filling it to this much pressure, okay, so how much gas I need to be putting in. Okay, so this is a useful information. So if there's a simple way, supposing I ask the question, if I would put this much moles of gas, okay, or this much mass of gas at this particular volume and temperature, what should be the pressure? If I have to ask this question, I can look up this table, okay? So, but that contains a lot of measurements, lot of data handling, okay? So you have reels and reels of pages, book of data, okay, just tables, all right? So that is not very, I mean, in the absence of anything else, that's okay, but is there a better way of thinking about this? Okay, so is there a more compact way of replacing a table of pressure, temperature, specific volume by a simpler equation? Okay, so by an equation itself, see, for many of these data, that an equation exists, it's not at all trivial. Okay, so a lot of reason why this, a lot of fundamental reason why such an equation exists. Okay, so that's, it's not, you can't take it for granted that there should be such an equation. All right, so but the search was on for such an equation. All right, so usually the way these things are found out is somebody did these experiments and then they saw a pattern, and that pattern, like for example Charles' law, Boyle's law, all these things, right? That pattern is what became a law. Okay, so not all laws, not all equations are the same. It's a pattern. Okay, it's named after the first person who notices that pattern, usually an experimentalist who could measure something, and then there was this pattern which was became a law. Right. So what is the simplest equation? You know this from your high school. It is the ideal gas behavior. Okay, so ideal gas is not a real material substance. Okay, certain gases, have this very simplistic, simple behavior in certain operational pressure and temperature. Okay, so you know of this when they behave, any gas may behave like an ideal gas. Okay, so what do you say? You say it's at higher temperature. Why is that so? Why does high temperature and low pressure makes the gas more ideal? So we know that the temperature is a measure of energy, right? Supposing what is that we want to avoid in a non-ideal gas, the interaction energy between gases is what makes the gas non-ideal, all right? So if you increase the temperature, go to higher and higher temperature. So what is actually being increased? It is the kinetic energy of the molecules or the gases is going to be increased, right? So higher the temperature, higher is the kinetic energy, and compared to this high kinetic energy in various degrees of freedom, your interaction energy becomes smaller and smaller. So in comparison to high kinetic energies represented by higher temperature, correlated to higher temperature, your interaction energies are much smaller. All right, so that's why most of the gases show an ideal gas-like behavior at higher temperature and low pressure. So for example, if you look at the data for water, so in this region, so let's say what we're plotting here is we are plotting temperature in the y-axis and specific volume in the x-axis at different pressures. Okay, so all three relevant variables are indicated here. So if you are having low pressure and you keep going to higher pressure and so on, right? So beyond a particular pressure, there is no region where no region in specific volume and temperature that the gas shows ideal gas behavior. However, when you are at low temperature and high pressure in this region, there is ideal gas behavior. Okay, so ideal gas is not a real substance. It is just an ideal gas behavior, all right? So this is for water. So what is the take-home message? The take-home message is the ideal gas behavior is seen here to a greater extent, that is at high temperature. As you decrease the temperature, the extent of ideal gas behavior also decreases, but there are also some regions where you at very low pressure. Okay, so corresponding decrease in pressure temperature has a lesser pressure associated with it. At very low pressures, you can still observe ideal gas behavior. But where is the non-ideal behavior? Around critical point. Okay, that's where a non-ideal behavior is there. Okay, so around in this region, for water vapor, in this region for any gas, there is no ideal gas behavior. So this is a useful diagram to have in your mind. Okay, so how do you non-ideality, like in people, is the reality of life. So you have to deal with the non-ideal behavior of gases. So how do you handle that? How do you manage non-ideality? Okay, so we introduce certain parameters, okay, to calibrate non-ideality, and you called the compressibility factor. We look into the origin of this word at a later stage, but for now, we'll define what you mean by compressibility factor. So if compressibility factor is 1, you call that an ideal gas. Anything away from 1, it can be more than 1 or less than 1, you call it real gas, non-ideal gas, non-ideal behavior. So you define compressibility factor with this simple equation. Okay, so V actual by V ideal. Okay, so this gives you the compressibility factor, and if it's 1, it's an ideal gas. So there's an interesting feature here. Okay, so you know where any gas. Okay, this behavior is general to any gas, not just to water and water vapor. So any gas shows this behavior. So where is it most non-ideal? So it is most non-ideal at the critical point. So, and the critical point is different for different gases, right? So if you take different gases at different pressures, but you normalize, okay, so the pressure with respect to that gas's critical pressure. You normalize the temperature with respect to that gas's critical temperature. You get what is called a reduced pressure. It has no dimensions and reduced temperature. What is very interesting is that there is certain universality in behavior. So what do you mean by this concept of universality? This is a term that is used often in physics. It is useful to understand. In different contexts, it may mean different things. But in this particular context, what you mean by universality is different gases behave in a similar manner when their reduced temperature and reduced pressure is just the same. Okay, so each gas might be does have different critical pressure and critical temperature. However, different gases with the same reduced, when you're operating at pressures and temperature, wherein the reduced pressure and reduced temperature is just about the same, then they all show similar behavior, okay, in terms of compressibility factor uh, and so on. Okay, so this is very interesting. Right? So here we are having a range of gases. Water vapor is a dipolar gas, methane, all these things are fairly different. CO2 is a linear molecule, right? Nitrogen is also not it's a covalently bonded homonuclear diatomic molecule, right? So you have a range of gases, and all these gases, if you plot the whole data, okay, compressibility data, in terms of reduced temperature and reduced pressure, all these things collapse. Okay, there's a data collapse. So there's an element of universality. Okay, so in terms of reduce pressure and reduce the temperature. Okay, so this is a useful thing to know. Again, so if you see, what is the theme? The theme is there is, to begin with, it's a diversity in experimental data. Okay, so we started with just a table of P, T, and V, right? Then what did you want? You wanted a simple equation, and in certain regimes you had an ideal gas equation. That's a great simplification here. Okay, that provided enormous data collapse, but that was not possible under most pressures and temperature. So you introduced this thing called compressibility factor. And in addition to compressibility factor, if you just plot everything under reduced pressure and reduced temperature, again, there is a data collapse. Okay, so this is an amazing thing, right? This is the way science works. You have diversity in data, there's some pattern, and then how do you, is there some compact way of representing this data? Okay, coming up with an equation and representing data. That's the way science works. It's very useful for engineering applications, all these things which we are discussing here, right? So, and then, okay, so you tried ideal gas, and that was not viable in many regimes. So is there something else? Okay, so so typically the first improvement over ideal gas is remembered, okay, because that is usually significant way of improving over some ideal system. Okay, so this is called van der Waals equation of state. So what did Mr. van der Waals do? Okay, so he had this notion that all gases had some finite size, right? So in ideal gas, we say that they're point-like particle. Okay, so there's no size associated with every gas molecule, gas atom. So van der Waals first said that there are finite sizes, even if you don't very precisely define the size. We can say that they have some finite size. Okay, so he introduced this notion and introduced an equation of state. Okay, so this B, this parameter B, for which is different for each gas, is indicative of the size of the gas. Right. Then what is this? Okay, this is it takes into account two kinds of interaction. Okay, if you have point particle, you don't have what is called excluded volume interaction. What do you mean by that? Okay, so you have a gas atom. If it has finite size, electrons are fermions, so you really cannot put one atom on top of the other. Okay, so if an atom is present at one particular point in space, position in space, no other atom can occupy that volume. Okay, this is called excluded volume interaction. And then there are electrodynamical interactions. Okay, so even at some level, excluded volume interaction is electrodynamics plus quantum mechanics, electrons being fermions and so on. Right. So this interaction which we are talking about is electrodynamical interaction. So what do you mean by that? If an atom is there, let's say noble gases are not that polarizable, but if you go to even noble gases, as you go down the rows, okay, in a particular column, as you go down, even for noble gas, they become more polarizable. Okay, so as a spherical charged, spherically symmetric noble gas, if you have a large noble gas atom, so they may get polarized as they come, okay, closer to each other. That is, the spherical charge distribution can become a dipole, and it can introduce certain kinds of interaction. Okay, so electrodynamical interaction. So again, that takes you away from ideality. Okay, and then how Van der Waals thought about that is, if you have a container, in the middle of container, it sees a symmetric environment. Or in the interior of the container, a particular atom is surrounded by many atoms. It sees more or less a symmetric environment. But if the atom is close to the container walls, okay, so on one side you have gases, on the other side you have the container wall. There is an asymmetric environment which introduces some certain kinds of effects, which changes the effective pressure, and that can go as a square of a system, goes as surface area. Okay, so that was why he introduced this term. So in a way, he included the finite gas, size of the gas, and then electrodynamical effects and excluded volume interaction. And then he came up with this. It had some intuition associated with it, and also some data. Okay, so he had some experimental data. And then in addition to that, what kind of experiment data gives you the value of A and B. Okay, so if you look at the behavior for all gases, they show this kind of a behavior when you plot, in this case, P and V, right? So there's an inflection point. So there is, this curve shows a particular kind of behavior in terms of its first and second derivative. With this first and second derivative inflection point, you can estimate A and B. Okay, so with that you can get these things for different gases. Okay, so it's a great, enormous amount of simplification. Okay, so getting into simplification associated with non-ideal gas. So actually, if you look at the data, it is not that the Van der Waals equation is very accurate. Okay, so the experimental data differs quite a bit from what you predict from Van der Waals equation, but it gave a good insight on liquefaction of gases. Okay, what gases can be more easily liquefied and so on. Okay, so that gave rise to very practical engineering applications and so on. So for developing this equation and other insights onto real gases, Van der Waals got a Nobel Prize in 1910. Right? So this is often beyond the ideal gas, maybe which you've seen from high school. This is the first equation of state, which is usually taught. Okay, so like with many things, you don't remember the second biggest person, right? For example, if you ask who's the second man on moon, okay, people remember Neil Armstrong, but people don't typically remember who's the second man on moon. Okay, so it becomes almost a matter of detail. Okay, so there are lots of equation of state. So there is one general feature. The first equation of state, Van der Waals had two constants, accurate over limited range. Okay, so it's not greatly accurate, but it gave some insight. Then few other people came in. They introduced more constant and more constant, more and more constants. Okay, so that's the story. Okay, so if you come up with more constant, you come up with the more accurate. You can name an equation of state based on yourself. Okay, so that is useful. Okay, so this is all. See, there are certain things like ideal gas that is useful for an introductory class like this. Okay, there's a pedagogical reason why we stick to simple systems like ideal gas and van der Waals equation. But when you go to real engineering application, okay, if you're so there, the elegant expression is not what matters. The accuracy is what matters. So it doesn't matter, especially with a lot of powerful computers, you can have fairly complicated equations with fitting constants and so on. That is useful. Okay, so there are lots of equations. We're not going to be dealing with any of this. But one thing which I want to be dealing, or at least you should be aware of, is what is called virial equation of state. Okay? So this has a particular utility. For example, here this is the data from the textbook. Okay, so it tells you temperature and accuracy of different equation of state at different temperatures and specific volumes. So it plots these equation of states and tells you, okay, so how accurate they are. But there is an equation whose accuracy can be increased depending on the number of terms you have. This is called what is called virial equation of state. This was not found by Mr. Virial. Okay, virial is a general term that comes from classical mechanics. There's a virial theorem and so on. So this is what is called a virial equation of state. You can have it's a power series. You can represent pressure of a real gas, a non-ideal gas, in terms of a power series. The more terms there are in this equation, the more accurate is your representation. These are called virial coefficients. Okay, this is all temperature dependent and so on. So even though this looks like a phenomenological or expression can be fitted, the data is fitted to experiments. In terms of statistical thermodynamics and mechanics, okay, statistical mechanics, you can interpret, okay, what do these virial coefficients mean? Okay, you can talk about two-body interactions, three-body interactions, and so on. The combinatorial and the way of computing these interactions can become complicated, okay, because there's something called cluster expansion and so on. The math can get complicated, as it is with most of the things in statistical mechanics and thermodynamics, but the interpretation becomes more sophisticated. Okay, that is, how do you take molecular information and then provide meaning to what you observe from macroscopic data? Okay, so not for particular things. So this Mayer cluster expansion was developed by Maria Mayer. So there are two Mayers. Okay, there's a famous book, I think it was written, an old book, 1942, called Statistical Mechanics by Mayer and Mayer. Okay, so it's a husband and wife pair. The wife got the Nobel Prize. Okay, she was the second woman to win the physics Nobel Prize. I suppose who is the first woman. Again, I will give you a clue. Both of them worked something in connection with nuclear physics. Okay, Maria Mayer developed the nuclear shell model, for which she was a theoretical physicist. She got the Nobel Prize for this work. Right. So this is something that is very useful in an engineering application that you should be aware of. We will do some problems related to equation of state in terms of these kinds of complicated equations of state, but simple equation of state like ideal gas equation of state and van der Waals equation of state is what we'll be using for most of the time in this class. With this, I will end this lecture.